Well, so we have discussed about eigenvalue and eigenfunctions. Okay. Now let us see one or two examples. So what is eigenvalue and eigenfunction? We have already discussed. Okay. If an operator operates on a well-behaved function to give the same function multiplied by a constant, then the function is called eigenfunction and the constant is called eigenvalue. Okay, and this is the operator function, same function, constant. So this constant is the eigenvalue and this function is the eigenfunction. Okay, now let us see. Say we have a function like this, say e to the power minus say 4x. This is the function, and operator is say d dx. Operator is say d dx. So you see, if we do this operation, operator fx equal to e to the power minus 4x. Okay, if we do this, what we get? Minus 4 into e to the power minus 4x. Okay, 4x. So operator function, same function, constant. So this is the eigenvalue and this is the eigenfunction. Okay, similarly you see, say um, say suppose fx equal to say sine x, fx equal to sine x. Okay, and if the operator is d dx, okay, d dx, if we do this, okay, suppose it is sine 2x. Okay, so what do you get? Okay, it is sine x, fx equal to sine x. Let me make it easier, sine x. So this is equal to d dx sine x equal to cos x. I can write 1 into cos x. So operator function, not the same function. Okay, so what we say? We say that sin x is not an eigenfunction with respect to this operator. Sin x is not an eigenfunction. Okay, because we do not get the same function. This is sine, this is cos. But if we do this, say d2 dx square sin x, this is equal to d dx and d dx sin x. So d dx sin x equal to cos x. So d dx cos x, and this is equal to minus sin x. So I can write minus 1 into sin x. Now what do we get? Operator function, same function, constant. Okay, so sin x is an eigenfunction with respect to this operator. Sin x is an eigenfunction with respect to this operator, but sin x is a not eigenfunction with respect to this operator. Okay, so what is the eigenvalue then? Eigenvalue is minus 1. Okay, so this is the example. Now, so we were basically talking about operators. Okay, we were discussing about operators. So we have discussed addition, subtraction of operator. We have discussed multiplication of operator. Then we have talked about commutator operator. Now there is another type of operator which is called linear operator. Okay, linear operator. Linear operator. So what is linear operator? We define like this. So we have an operator, and we have two functions, fx and gx. We have two functions. We have an operator and we have two functions, fx and gx. Okay. Now if we can write like this, if this is possible, say fx plus gx equal to O fx plus O gx. If we can write like this, if this is possible, then the operator is called a linear operator. If this is possible, again this is one condition, again another condition, say this operator and constant, say we have a constant c fx. C is a constant, and this is equal to C O fx. Okay, so either this condition or this condition is satisfied. C is a constant. Okay, if either this is equal to this or this is equal to this, then we say that then the operator O cap is linear. If this is possible, if this or this condition is satisfied, then the operator is linear operator. Okay. For example, say multiplication. We have two functions. Let me see this. Say multiplication by x. Multiplication by x operator. What is the operator? Multiplication by x. And fx. Fx equal to say x square. Okay, this is the operator. What is the operator? Once again, multiplication by x. Fx equal to say x square, and gx equal to say x cube. Okay, so operator x square plus x cube. Okay, fx plus gx operator. So definitely we can write like this: x into x square plus x into x cube, that is equal to x cube plus x to the power 4. Definitely we can write like this. So multiplication is a linear operator because they are equal. Similarly, suppose d dx x square x cube. Now operator is d dx fx x square gx x cube. So we can write like this: d dx x square plus d dx x cube. We can write like this. This is possible. This is okay, all right. This is possible. So again, we can do this: 2x plus 3x square. We can do this, but this is possible. We can write like this. So again, d dx is linear operator because we can write like this. But say taking square root. Now our operator is taking square root. Square root of x square plus x cube. Can we write like this? X square. Can we write like this? No, this is not possible. This is not possible. So taking square root is not linear operator. Okay, because this is equal to not this. Now operator is taking square root. Fx, gx, this is not equal. So taking square root is not linear operator. Okay. So this is a linear operator. Similarly, if you take log, suppose we are taking log. Say log. Now what is the operator? Operator is the taking log. Say log x square plus x cube. Can we write like this? Log x square plus log x cube. Can we write like this? No, this is not possible. This is not possible. Okay, so again taking log is not linear operator because they are not equal. Alright, so there are some linear operators, but there are again some non-linear. Okay, so in quantum chemistry we are basically interested in linear operators. Okay, linear operators. Now next is the operator delta and del square. Actually this is not del, actually this is not del, but we call it del. Okay, this. Now what is del operator? What is del operator? This is equal to I d dx. Actually this should be partial differentiation plus z del y plus k del z. Okay, k del z. I j k, these are unit factors. I j k, these are unit factors. Okay, unit vectors. I j k are unit vectors. Okay, so this is del operator, and using vector we can prove that that's equal to del 2 del x square plus del 2 del y square plus del 2 del z square. We can prove this. Okay, so these are del and del square operators. Okay, this is also called Laplacian operator. This is also called Laplacian operator. Okay, this operator is called Laplacian operator, del 2 Laplacian operator. Okay, then there is another type of operator which is called Hermitian operators. Hermitian operator. This is another type of operator. Okay, Hermitian operator. Generally, how we define Hermitian operator? Okay, how we define Hermitian operator? Suppose, say we have this function, say psi n. We have this function, and operator is this. We have this function and operator is this. So if say integration psi n star o psi n d tau is equal to integration psi n star o psi n d tau whole star. so that I can write it like this. So that I can write it star complex conjugate again complex conjugate. So this will be psi n, and this will be O psi n complex conjugate d tau. If this is equal to this, then the operator is called a Hermitian operator. If this is equal to this, operator is called a Hermitian operator. Okay, so this is definition of Hermitian operator. Now we can have another definition also. Let me tell you, and that definition is in terms of two functions. Okay, in terms of two functions. Suppose we have two functions. Suppose we have two functions and one operator. Okay, this is one definition of Hermitian operator. This is equal to this, then operator is the Hermitian operator. Or we can define like this. Say we have this, then say psi m complex conjugate O psi n d tau, and this is equal to psi n O psi m complex conjugate d tau. Okay, so definition of Hermitian operator can be given like this, or it can be given like this. Okay, so here also this operator is called the Hermitian operator. Here also this operator is called the Hermitian operator. Okay, these are the two conditions, Hermitian operator. Now once again, in quantum chemistry, the operators we use are Hermitian operators. I repeat, in quantum chemistry, the operators we use are Hermitian operators. So we will discuss about that later, but just remember that in quantum chemistry, we will be using some operators, and these operators are Hermitian operators. That means either this is equal to this or this is equal to this, Hermitian operators. Okay, so this is Hermitian operators. So these are the different types of operators. Now here let me tell you about one condition. So this integration, this symbol, this integration we can write like this. Okay, we can write like this, or simply we can write like this. Okay, now this is called bracket notation. Okay, this is called bracket notation. So you need not have to worry. This integration means this or this. Just symbol only. Okay, just symbol only. Actually, here there are two things. One thing is this. This is called bra. And this thing is called kit. Okay. So in general, this is called bracket notation. Similarly, this integration, say integration psi m O psi n d tau. So we can write it like this. Either we can write it like this, psi m O psi n or we can write like this, M O N. We can write like this, bracket notation. So don't worry about this. This is just symbol only, nothing else. Okay, this is another form how to represent. So Hermitian operators. Now let us talk about postulates of quantum mechanics. Okay, postulates of quantum mechanics. Quantum mechanics. Postulates of quantum mechanics. Let us talk about this. Okay. Now, so there are some actually basic postulates. Okay, basic postulates which are generally followed in quantum mechanics. Okay. Number one postulate is that the state of a microsystem, the state of a microsystem is represented by a function of coordinates and time, and which is called the state function, or simply state. We have already talked about this basically. This is the state function, and we have seen that state function is a function of coordinate and time. So there is nothing new in fact. We have already talked about this. Okay, so this is the first postulate. Second postulate is that each physical quantity, this is a physical quantity, it is also called dynamic variables, is represented by an operator in quantum mechanics. So in quantum mechanics, each physical quantity is represented by an operator. So we have already discussed about operators. Okay, now why we need operator? Because in quantum mechanics, physical quantity will be represented by an operator. That means by a mathematical operation. Okay, so each physical quantity is represented by an operator in quantum mechanics. Okay, so this is important. Now, so that means we have to write physical quantity as operator. Physical quantity is also called dynamic variable. Now, how to write physical quantity as operator? Physical quantity as operator. Okay, how to do this? So there are two steps. First, what you do, express the physical quantity. In terms of momentum momentum and or coordinates. This is the first step. You have to express the physical quantity in terms of momentum and coordinates. Okay. And second step is that replace momentum coordinates by the corresponding operators. Well, let me explain this. So first is simple. We have to express the physical quantity in terms of momentum and coordinates. Then second step is the replace momentum and coordinate in terms of corresponding operators. Now, what are the operators for momentum and coordinates? What are the operators for momentum or coordinates? Let us see that. Say operator for coordinate. Operator for coordinate. This is nothing but suppose we want to talk about x coordinate, then you multiply by x. Okay, x coordinate operator. What is the operator for x coordinate? Multiplication by x. What is the operator for y coordinate? Multiplication by y. What is the operator for z coordinate? Multiplication by z. So simple. Operator for coordinate means multiplication. Okay. Now what is the operator for momentum? Operator for momentum. Operator for momentum. Now operator for say x component of momentum. This is momentum. In physics, how we write momentum? Say in physics, we write momentum as say x component of momentum. That is equal to mass into x component of velocity. Okay, y component of momentum. This means mass into y component of velocity. Okay, but in quantum mechanics, we cannot write like this because for each physical quantity we have to write operators. For each physical quantity we have to write operator. So in quantum mechanics we cannot write like this. How we write like this? Say x component of momentum, we will write like this: h bar by I del x. Y component of momentum, h bar by I del x. And similarly z component, h bar by I del z. So you remember this. Now how we get this? That is reason. I am not going to discuss about all those things. Okay? Just remember that operator for momentum, this x component, y component, z component, h bar by I del z. Okay? Now let us see how we write the operator for physical quantity. So suppose kinetic energy in x dimension. Okay, so suppose T, let me represent kinetic energy by T, x dimension. So in physics, how we write like this? Half mvx square. This is the kinetic energy in x dimension. Now, what is the first step in writing operator? In writing operator, what is the first step? We have to express the physical quantity in terms of, say, momentum. So how we can do this? I can write it like this: 1 by 2m m square vx square, that is equal to 1 by 2m px square. Okay, so we have expressed the physical quantity. In terms of momentum. Okay, so this is the first step. First step is done. We have done the first step. So now second step, we have to replace momentum by the corresponding operator. Okay, so now operator, we are writing the operator. So I write cap. We are writing operator, so I write cap. Okay, operator. This is equal to 1 by 2m. What is px? H bar by I del x. So h bar by I del x square. So this is equal to I square equal to -1. So this is minus h bar square by 2m del 2 del x square. So this is the operator. This is the operator for kinetic energy in x dimension. Operator for kinetic energy in x dimension. Okay. Similarly, operator for kinetic energy in y dimension will be minus h bar square by 2m del y square. Del y square. Now total kinetic energy equal to Tx plus Ty plus Tz, 3 dimension. And if we write the operator, so we can write like this. Minus h bar square by 2m. So I can write like this: del 2 del x square del 2 del y square del 2 del z square. Okay, and we have already seen this is Laplacian operator, so we can write it like this: minus h bar square by 2m del square. This is Laplacian operator. This. So this is the operator for total kinetic energy, operator for kinetic energy x dimension, y dimension, similarly z dimension. Okay, operator for kinetic energy. All right. Now here you remember one thing. If we consider more than one variable, here we have 3 variables: x, y, z, 3 variables. So when we have more than one variable, we write partial differentiation. But if we consider only one dimension, suppose we consider kinetic energy only in x dimension, we are not bothered about other dimensions, then we can just write simple differentiation. d2 dx square. If there is only one variable, then we will write simple differentiation. Okay, but if there is more than one variable, we will write partial differentiation. Okay, so this is operator for kinetic energy. Now let me see operator for total energy. Operator for total energy. Now total energy equal to kinetic energy plus potential energy. total energy equal to kinetic energy plus potential energy. So what will be the operator? Operator will be kinetic energy. If we consider only one dimension, minus h bar square 2m, then we are considering only one dimension. Kinetic energy, operator for kinetic energy, and let me write potential energy as V. Okay, let me write potential energy as V. So this is the operator for total energy in x dimension. This is the operator for total energy in x dimension. An operator for total energy is called the Hamiltonian operator. H. Operator for total energy. Operator for total energy is called the Hamiltonian operator. So Hamiltonian operator is equal to this. This is in x dimension. Similarly, in 3 dimension, Hamiltonian operator will be equal to minus h bar square by 2m. Now partial differentiation. Let me write potential energy as V. Okay. So this is the operator for total energy in 3 dimension. We are using partial differentiation. But if we consider only one dimension, we do not use partial differentiation. Now you see, operator for total energy is written as H, whether it is in 1 dimension, 2 dimension or 3 dimension. I repeat, operator for total energy is represented as H, Hamiltonian operator, whether it is in 1 dimension, 2 dimension or 3 dimension. Okay, so operator for total energy. Next, let us see another thing, operator for angular momentum. Operator for angular momentum. Operator for angular momentum. Okay. Now, what is angular momentum? Suppose one particle is rotating along a circular path. One particle mass m, it is rotating along a circular path of radius r, circular path of radius r. So it will have angular momentum. And we know in physics what is the angular momentum? This is equal to mvr. V is the velocity. Okay. Now, in terms of vector, how we represent angular momentum? In terms of vector, angular momentum is represented by this. This is cross product. This is vector cross product. Okay. Suppose this is the radius vector, this is the momentum vector. Now, if I draw the circular path like this, that means this circular path is on the plane of the paper. Now, if I draw the circular path like this, perpendicular to this, then I can write it, and then I can draw it like this. Okay, this is this same circular path. This is on this plane and this is on this plane. That is the difference, on this plane. Okay, so this is the radius vector, this is the momentum vector, and angular momentum vector. Angular momentum vector is this. Angular momentum vector is this. That means angular momentum vector is perpendicular perpendicular to the plane formed by radius vector and momentum vector. So radius vector, momentum vector, they are on the plane of the paper. So angular momentum vector is perpendicular to this, okay. So this is angular momentum, and in terms of vector, this. So since this is vector quantity, it will have components. So I can write in terms of unit vector like this: I Lx plus J Ly plus K Lz. So this is a number 1. I can write like this: I J K unit vectors Lx, Ly, Lz. These are the components of angular momentum along x, y and z axis. Lx is the component of angular momentum along x axis. Ly, component of angular momentum along y axis, and so on. Z. Okay. Now, similarly, radius vector, it also can be represented like this. Say x, z, y, k, z. Similarly, momentum vector, it can also be represented like this: I px, z py, k pz. It can also be represented like this. So if I r cross p, that can be represented in terms of determinant: I j k x y z px py pz. R cross p can be represented in terms of determinant. So if we expand this, then I, okay, ypz minus zpy, ypz minus zpy, okay. Then plus z. I am writing plus, not minus. If I write plus, so this zpx minus xpz, zpx minus xpz plus k. So it will be xpy minus ypx. Okay. So from r cross p we get this result. Okay. So this is a 2. Now if you compare 1 and 2, L, Lx, see, J, Ly, J this, K, Lz, K this. So comparing 1 and 2, okay, what we get? 1 and 2, what we get? Lx will be equal to ypz minus zpy. Ly will be equal to zpx minus xpz, and similarly Lz. Okay. Now what we have actually done? We have expressed angular momentum in terms of coordinate and momentum. That means we are doing the first thing. We are expressing the physical quantity in terms of coordinate and momentum. I repeat, we are expressing the physical quantity in terms of coordinate and momentum. So by doing all these things, we have expressed the physical quantity in terms of coordinate and momentum. Okay. Now second step, replace. replace coordinate and momentum by the corresponding operators. So if I do this, say Lx, now operator, all x. Operator for coordinate, that means multiplication by y. Coordinate, operator for coordinate is multiplication by y. And this h bar by I del z minus similarly z into h bar by I del okay. You can take h bar by I common, okay, and you can write this. So this is how we write the operators for physical quantity, okay, physical quantity. So this is operator number 2. So what is the second operator? Second operator is that we use operator for each physical quantity. This is the second postulate. Now third postulate is postulate 3. The possible value of a physical quantity is given by the constant lambda in the equation O psi equal to lambda psi. Okay, the possible value of a physical quantity. Okay, let me add something. Represented by operator O cap. The possible value of a physical quantity represented by operator O cap, okay, O cap, is given by the constant lambda in the equation this. Okay, so we have already said that physical quantity is represented by operator. So value of the physical quantity, and that physical quantity has been represented by this operator. Okay, for example, say this is the operator for total energy. Okay, and this is the function, operator for total energy. This is the function, and say lambda psi, okay, and this lambda will give the value of total energy represented by Hamiltonian operator. Okay, and we can write it like this, E psi. Okay, because Hamiltonian operator represents total energy. So value of the physical quantity, that is total energy, is obtained from the constant in the equation this. Value of the physical quantity represented by the operator. Is given by the constant in this equation. And this type of equation is known as eigenvalue equation. eigenvalue equation. Eigenvalue equation. What is eigenvalue equation? Operator, function, same function multiplied by a constant. This type of equation is called eigenvalue equation. Okay, this is eigenvalue equation. Next, postulate 4, fourth postulate. The expectation value of a physical quantity of a system whose state function is psi, is given by say this is the expectation value, say physical quantity. Let me represent the physical quantity by m. Physical quantity is the m, and expectation value means average value. Expectation value, average value of a physical quantity. Average value is represented by this symbol. Okay, and this is equal to, and for the system wave function is psi, so we write it like this, psi, and this is the operator for the system. Operator for the system. Here you see, if psi is real, we write like this. But if psi is imaginary, we have to write like this. Because for real function, psi star complex conjugate will be equal to psi. Okay? For real function, say e to the power mx, this is real function. So psi star equal to psi equal to e to the power mx. But if e to the power ix, if we get this, okay, if psi equal to this, then psi star will be equal to e to the power minus ix. If the function is imaginary, psi and psi star are not the same. But if function is real, psi and psi star are the same, no difference. So if the function is imaginary, we have to write this, and if function is real, we will write just psi. You can write like this, but since they are equal, so we can write psi also. Okay, so average value of a physical quantity. Suppose average value of momentum in x dimension. How we write like this? Psi star momentum. What is the operator for momentum? H bar by I. D I am taking only in x dimension. D and psi d. Now this is dx. Since I am taking only x dimension. Okay. Now you know, when I write d tau, then it means dx into dy into dz. At the same time, it means minus infinity to plus infinity. But here I am to write limit. Okay. Yes. Psi star psi theta minus infinity to plus infinity. Okay. This. So This is the physical quantity, momentum. This is the physical quantity, momentum. So what is the operator for momentum? Operator for momentum is h bar by I. This is the operator for momentum. Okay. Similarly, say average value of total energy. Again, this is given by say psi h psi d tau psi d tau. I assume psi to be real. So we can write like this. Or you can write complex conjugate also, no problem. You can write complex conjugate. So average value of physical quantity. Okay. Now there is 1/5 postulate, which is nothing but Schrödinger's time dependent equation. This is nothing but Schrödinger's time dependent equation. So basically these are the postulates of quantum mechanics. Okay. So we have discussed about the postulates of quantum mechanics. Now let me see what I can discuss. Let me see. Okay. So so these are the basic things. Okay. Basically, these are the basic things which we have to study well. Okay. So after this we will go to some specific examples, just like particle in one-dimensional box, particle in three-dimensional box, and so on. But here let me solve some problems. Just like, say you have been asked one question, suppose show that this is equal to let me see, I h bar. Okay, I h bar. Okay, not this. Show that x px equal to I h bar. Let me see. Okay, x px. So this. Now we have to prove this. This is equal to this. Now what is this? This is commutator operator. You know, this is commutator operator. Okay. So what is this? This is commutator operator. Okay. Here you see no function has been given. With operator we need some function. So you just take any function. Suppose function is psi. We take the function to be psi. So what we do? We write like this. Say x, what is px? Px is equal to h bar by I d dx psi. Okay, px equal to h bar by I d dx psi. So now what is this? This is equal to x into h bar by I d dx psi. Okay, a b, this is a, this is b, a b, so this minus b a, so a b, now b a psi. Okay, B A psi, A B psi minus B A psi. Okay, now if we do this, x, let me write it like this, h bar by I d psi dx minus, now we have two functions, you see, we have two functions. So this is equal to h bar by I d dx, first function, second function, first function, second function. So d dx of x into second function plus first function into d dx of second function, second form. Okay, so this is equal to x h bar by I d psi dx minus, so dx cancel, so this is h bar by I psi minus x into h bar by I d psi dx, okay, so this cancels, so this is equal to, I can write it like this, minus h into I square psi, so I square equal to minus 1, so this is equal to I h bar psi. Okay, so this is equal to this, so psi, so x px must be equal to I h bar. So we can prove like this. Okay, we can prove like this. So anything else which I can discuss? I think I should stop here. Next time we will discuss about applications. Next time we will discuss about applications of applications of Schrödinger equation. Applications of Schrödinger equation means we will write Schrödinger equation for a system. We will write Schrödinger equation for a system, and then we will try to solve it. That is application of Schrödinger equation. And let me discuss another thing. Let me see another example. Rather very small problem. Let me see if I can find out. Okay. So another question. Say if psi 1 and psi 2 are two degenerate eigenfunctions of the linear operator O cap, then show that the linear combination of the two functions is also an eigenfunction of the operator of the operator with the same eigenvalue. Okay, so what is the question? Psi 1 and psi 2 are two degenerate eigenfunctions. Degenerate eigenfunctions of the linear operator. O cap. Okay, then show that the linear combination of the two functions, is also an eigenfunction of the operator, of the same operator, having the same eigenvalue. We have to prove this. Now, first condition is that these are the two eigenfunctions of the operator this. So I can write eigenvalue equation. Okay, I can write eigenvalue equation. So suppose this is the operator. And function is psi 1, and let the eigenvalue be lambda psi 1. Okay, so linear operator, eigenfunction, and this is the eigenvalue. And what has been said? They are degenerate. Psi 1 and psi 2 are degenerate. That means they are having the same energy, same eigenvalue. That means same eigenvalue. So these are the two conditions. Okay. So these are the two conditions. Psi 1 and psi 2 are the eigenfunctions of the linear operator. This is linear operator, mind that. This is linear operator. And okay, degenerate eigenfunction, same eigenvalue. So linear combination of the two functions. That means linear combination of psi 1 and psi 2. That means C1 psi 1 plus C2 psi 2. This is the linear combination. Okay. Now, linear combination of these two functions is also an eigenfunction. That means eigenfunction of this having the same eigenvalue. That means this C1 psi 1 plus C2 psi 2. So we have to prove that. So we have to prove this. Okay, linear combination of these two functions is also eigenfunction of the operator. Having the same eigenvalue. That means this condition must be satisfied. Okay. Now how to prove this? Now here left hand side. You see the left hand side. O C1 psi 1 plus C2 psi 2. This is linear operator. So since linear operator, we can write it like this. C1 psi 1 plus O C2 psi 2. We can write like this. Because linear operator. If O were not linear operator, we could not have written like this. Since O is linear operator, we can write like this. Again, linear operator. So how we can write this? C1 O psi 1 C2 O psi 2. Because linear operator. This is another condition of linear operator. Constant. These are constants. Linear combination. In linear combination, they are constant. So we can write it. Now O psi 1, O psi 2, O psi 1, lambda psi 1. So C1 lambda psi 1 plus O psi 2 lambda psi 2 C2 lambda psi 2. So what we can write? lambda, I can take lambda constant, C1 psi 1 plus C2 psi 2. So this is equal to this. So proved. This is proved. Okay. So we can prove this way. So let us stop here. Okay. Next time we will discuss about the applications of quantum mechanics. Okay. Thank you.